Hello, everyone. Hi, I'm Will Heslam. I'm a token JavaScript developer here today at Lambda Days, and it's a pleasure to be here. Please bear with me, as this talk is fairly new and may need some extra polish. Taka Graswolf. That's meant to be broken Polish for, pardon the pun. I don't know if that came across. It's fine. I'll just drop the jokes. It's fine. I'm here to show everyone that you can do functional programming in even the lowliest of languages, JavaScript. Only joking. There's actually tens of functional JavaScript developers now. I can see some of them in the audience there. There you go. Yeah, cool, fantastic, excellent. So I'm a developer at Ecotricity. It's a British company. We're a green energy company. And we're using JavaScript to implement our backend services, essentially. We're using AWS Lambda, so everything's just JavaScript functions plugged into stuff. And typically, the kind of code we write for a service would be a function that, say, listens to an API call, writes to a database, puts a message on a queue or a stream, and then sends a response back to the user for whatever reason. And a lot of these are best effort, okay? So for example, Amazon's database that they often encourage you to use is DynamoDB, and that can be under-provisioned or over-provisioned. It can run out of bandwidth effectively. It can throw messages back at you and say, I'm too busy to handle this. It's also not entirely consistent all the time. It's not always available. So, and streams or queues can be full, for example. So there's all sorts of situations where you don't know that your operation you're trying to do is going to succeed or fail. So you have to take that into account. So how can we model these kind of side-effecting dependencies in a way that will give us confidence that our code will be robust in all these different scenarios? And bear with me, because I've got two clickers, one for my notes and one for the screen. So hopefully they'll sync up, and I have to do it two-handed. Cool, all right, yeah, there we go. So this talk is split up into three sections. Number one, property testing, which is where I'll explain what property testing is and why it's valuable. And then I'll explain a concept called Extensible Effects, why that might be useful, what kind of impact it might have on your code if you write that way. And at the end, we'll tie it all together and show you how to do property testing with extensible effects, if you can imagine such a thing. On the way we'll be introduced to some monads, and we'll learn how to use them, and it'll be fun. Let's go. Part one, property testing. A refresher, very quickly. Who here unit tests? Hands up. Okay, good. That's actually pretty much most people. Anyone who doesn't, feel free to leave now. We'll just turn away. I'll give you a minute. Okay, good. So lots of people unit test. How many people have heard of property testing? Okay, pretty much everyone. So I'm not going to spend too much on the bit where I explain what property testing is. That's fine, that's a good thing. So very quickly, most people have used example-based testing. They would typically refer to that as just unit testing. Example-based testing this is my analogy for it. It's a Nerf gun that fires one shot, okay? So you put in A, you expect B, you get back C, your test fails. So it's very precise, but you do one thing after the other, and that's pretty much it. If you're trying to fight a war, this single Nerf gun's not going to scale, right? It's not going to work for hundreds and hundreds of different tests. You have to write them out all one after the other. This is my metaphor for property testing. Yeah, that's more like it, right? So in this case, you're not firing single values in and then checking what you get back out. You're spraying your tests with hundreds of different values, maybe even thousands. And you're checking not that if 2 plus 2 isn't 4, then fail the test. Instead, it would be something like, I'm going to try and come up with one on the fly. Any positive integer plus any positive integer is always greater than those two integers you put in, right? That sounds sensible. The other nice thing about it is that property testing is that the libraries that implement this and allow you to do this kind of testing will, if they find a failing case, so let's say there's a special number that actually is a positive number but also makes your number go down. It could be maybe overflow, maybe your number's too big, right? That would actually be a perfect example of a property test would find that for you. It will then find the minimal edge case. So instead of adding 100 billion to 100 billion, it would try, okay, what about 9 billion 999 million. And it would keep trying smaller and smaller cases until it finds the smallest possible still failing case, which is great because you don't want to be looking through some giant, massive data structure when actually there's a simpler failing case that could be reported to you. John Hughes is the co-inventor of property testing. He's actually, he's doing a talk after this one about property testing, so don't miss that. It's probably going to be better than this one, but that's fine. You're here now. So he wrote a fantastic paper called Experiences with QuickCheck, Testing the Hard Stuff and Staying Sane. QuickCheck is a Haskell library for doing property testing. We're not going to be using QuickCheck because we're going to be doing this in JavaScript, and there's a different library for that. But he said that one of the fundamental problems with unit tests is, well, first of all, they're quite brittle. You have to write loads of them. And more damningly, you can never be done. You never know. If I tried every possible combination. So here's a classic example. Even if you've got code coverage that says, hey, you've covered every single branch, every condition, every statement in your code, you're doing A divided by B. Well, you may have tried B being 2 and 10 and 100, but did you ever try B being 0? Well, now dividing A by B is a division by 0. Depending on your runtime or your language, that could be not a number value, or that could be an exception, could be anything, right? So even though you thought you'd covered all your eventualities, actually there was this time bomb sitting ready to go off. So yeah, we're going to introduce our first monad of the afternoon, which is the arbitrary or gen monad, which is how you build your property tests. It's central to the idea. This is a data structure that allows you to describe spaces of values, okay? So a classic one would be any possible string, or every possible number, or every possible array of every possible number. You can then chain these together, so you can say, I want to take every possible number and then build an object out of it that has that number as a key, but the value could be something else. That's a really contrived example, but you get the idea. Let's see an example. So this is building a unique set. We're using a library called FastCheck here, which is a fantastic property testing library for JavaScript. If you don't know of it, you should know of it, because it's fantastic, it's good. The other ones are less maintained, to be honest, and this one's got a nice user-friendly API. We're building a unique set of the following values, A, B, C, and D. Can move that out of the way. Here we go. And we then generate that unique set of A, B, C, or D as a variable length array, and then we randomly shuffle it and delete some. That's what the chain's doing there. Sample it, you get BA, an empty array, CBA. Okay, so it's fairly straightforward. Let's look at how you'd use this in a real example. So let's say we're writing a backend service that processes a number of events that come in. And we want to make sure that we always process them in a specific order, or we might get some weird accounting problem. Maybe we, I don't know, try and subtract money from someone's bank account before we've added some money in, or try and, I don't know, delete someone's account before they've signed up, something strange like that. You've got to make sure that your event's always processed in order to keep the logical consistency. This is a good way of doing it. You've got events come in with 3 fields, date, type, and priority. And we want to make sure that we always sort them in priority order. Well, subtracting A from B there. Let's build a property test to check that that actually works. This is our test. Looks like a lot of code, but it's fairly straightforward. Let's go through it step by step. So we're building an array of records here where you've got a type field, a priority field, and a date. The date is any random date from 1970, I think it can even be 1969, up to whenever dates run out. You've got priority, which is any natural number. That's the one we're actually interested in sorting by. And then you've got the type, which is either foo, bar, or baz. And let's look at how we're chaining that. We're then taking that random set of events, shuffling them, and producing a new object that has the original set of random events and then a shuffle. So it's not deleting any, it's the same size array, but it's shuffling them randomly in place. And this is the beautiful bit. The test is really simple. It just says, if you order the original one by our sorting function, and then you order the shuffled one, they should always come up with the same result. The beautiful thing about a good property test is when the body is a single line like this, in my opinion anyway. So it will, by default, run 100 times, and you can change that, but let's see what happens. Lo and behold, it's found a failing case. That's good, otherwise this talk would have been a bit short. So what's happening here is it's pointing out that the original and the shuffled version gave you back two different results. The date in one was the other way around. Okay, so there's a problem with our sorting function. Let's try and fix this. Okay, so now we decide if the priority, subtracting A from B, is 0, i.e. they have the same priority, let's use something else to sort by. In this case, we're going to go by date. We're just going to pick the one that has, I guess, the earliest date and say, hey, that's the most important one. So let's run the test and see. Oh, it fails again. Why is that? That's interesting. Now, this time it's saying, well, actually, look, I'm ordering it by date and priority, 1717, 1969, well, second before the Unix epoch there, but the types are different. As in, the ordered and the original and the shuffled versions had them in reverse order, and our sorting function didn't deal with that. So let's go back and fix this for good. So now we're going to check if the dates are the same, if that comparison, then we're going to pick a priority based on the event type name. Does that make sense to everyone? Okay, let's see if we've ensured a total ordering now. Hey, it succeeded. Fantastic. That's great. So now we've got a property test that proves that we've got a total ordering. Our sorting function handles anything that you can throw at it. So that's a really simple example of how property testing can really easily not only find corner cases you hadn't considered, but it doesn't even have to be that complicated. So that's kind of it, really. That's property testing. Now, before I want to go on, I want to say that there is an art to building good generators. I call it the description is not the recipe. That's my catchphrase. It's not a very good one, but it is mine. And the idea is that let's say you want to generate 1,000 even numbers. Could be random, but they'd have to be even. You could use FastCheck's natural number generator and then filter out anything that doesn't modulo 2 to 0. The problem with that is it'll generate 2,000 random numbers and filter out half of them, roughly speaking. Whereas the bottom one here, you're generating random numbers, then you're just multiplying by 2. So that's producing even numbers rather than filtering them out. So you'll get 1,000 numbers will turn into 1,000 even numbers. So it's twice as efficient, more or less. My metaphor for this is if you're trying to put together an iPhone building factory, okay, you could just get all the parts, bits of metal and glass and plastic, and put them in a big plastic box and just shake it. And go, is that an iPhone? No, get rid of it. Shake. Is that an iPhone? No, get rid of it. Or you could follow a recipe. And the recipe means that you'll get an iPhone 99% of the time, and then you throw away the defects, rather than trying randomly to produce something and then throwing away anything that doesn't look like what you're looking for. So yeah, now you've learned a bit about property testing and how it might be useful. Let's move on to part 2. So in this case, we're going to be looking at extensible effects. Now, extensible effects, I want to elaborate on. I want to give you a concrete example because it's a fairly involved category theory idea. I don't fully understand the academic side myself. I kind of want to show you a practical example. So we're going to look at a simple JavaScript function, see how you would test it, and see whether extensible effects can help or hinder you in testing your JavaScript function. And the best kind of thing to build if you're introducing a new paradigm or library is a to-do app, obviously, right? Everyone loves to-do apps, except it looks like there's lots of to-do apps. So instead of building a front end for a to-do app, we're going to build a backend. And actually, the backend is just going to be an API that receives an array of to-do items and then writes them to a database, and then tells you, hey, did they get actually written to the database, or were they invalid or not? So this is a fairly straightforward function. I've color-coded it, which should help. Green is the bit where we're listening for put requests to an update URL. Blue is where we're writing those items to the actual database. And that's yellow. It's not particularly obvious it's yellow. And that's responding to the client saying, hey, look, I wrote all of these items to the database that had titles. If they don't have titles, there's no unique key for me to put them in the database, so I haven't added them. So that's a fairly straightforward function. Does everyone agree? It seems like it should work. How would we test it? There's two traditional ways you would test a function like this. We're going to look at the first one, and we're going to discuss the pros and cons. The first one is going to be mocking. So in this case, I've color-coded it again to show you which bits of the original function, handling events coming in, writing to the database and responding, are being mocked or otherwise dealt with by this test here. You can see that we're mocking our API put request with a fake API. We're mocking the database in blue, returning a resolved promise, representing a successful database batch write. And then we're simply invoking a really simple set of to-do items there. You've got, if you're hungry, you've got to buy hummus, right? And then also, you've got to make sure you finish your Lambda Days talk. Can't forget to do that. And what did we get back? Well, we got back a message, HTTP status code 200, everything's good. And it added the buy hummus to-do item, but it didn't add the finish Lambda Days talk item because there was no title. And if I'd known that, then I probably wouldn't have forgotten to finish my Lambda Days talk, right? So always make sure that you've tested your functions. Yeah, the problem with mocking, in my opinion, is that, it often relies on global mutation, effectively. This point here, up at the top, we're mocking our API and our database. Well, that implies a form of a sequence that has to, an implicit sequence that has to be kept to. This prevents you from running all of your tests concurrently, and then that also prevents you from running them in parallel. So it slows down your tests. You've got to make sure that you set up your mocks and then at some point tear them down. So now your test run is more complicated because it has to have a before or an after block or something like that where you can set everything up, tear it all down. If you forget to mock something, you're going to get weird errors. There's a classic story, I don't know which company fell afoul of this, but there was a startup that had integrated their app with a messaging API, and they had someone complaining to them that they constantly got texted by this company. Every day, lots of text coming in, marketing to him, and he was really annoyed about it. So they went in their database, and they went through all the rows looking for this. Is this person's phone number in the production database? Yeah, let's get rid of that there. Let's make sure he's not signed up. Delete, delete, delete. Go in the dev database, make sure he's not in there as well. Turns out that it was just being used as dummy data, his phone number, and they'd forgotten to mock their integration with the texting service. So every time a developer committed and pushed up to their CI, this guy would get a text. So that's obviously an egregious example, but it kind of just shows the point that bad things could happen if you don't explicitly mock all of your dependencies. And furthermore, all your dependencies here are implicit. Okay? There's nothing about our function service update that tells us in the type signature or in the names that it uses a batch write function on our database. There's nothing that tells us it listens to the update URL on the put API. So you just have to know that. And that might be fine. You can put it in the JS doc. But let's say I built this, and then I go on holiday, and someone else comes and adds a new feature. I come back, run the tests, and suddenly I'm not mocking that. Maybe they've removed the batch write. Maybe it's now adding items individually. But we left the mocking feature in. So now it's mocking a part of the database we never even use. So it has this kind of implicit dependency which can cause problems. The pros, there are plenty of pros, is that your function is left relatively unchanged. You don't have to change your code in order to test it. That's a really nice thing about this. So there are definite pros and cons, and also it's fairly succinct. That's another advantage. And let's look at the alternative, which would be dependency injection. So dependency injection, and this is broad terms, I mean, there's 1,000 ways to do this, but dependency injection is the idea that instead of having some global dependency or import you're relying on, you pass the things you're going to use into your functions as values, as arguments, and then your function just uses them as you might expect. There are several, so I'm a fan of dependency injection myself, but there are actually several downsides. The downsides would be that, well, first of all, it means you have to change your source code. You have to make sure that every time you want to use one of these dependencies, you thread it all the way through your call stack, all the way down. And that can bloat your code. It can make things more confusing. Names become a bit more vague. If you're passing in, if you're writing to an interface rather than a concrete implementation, suddenly it's not DynamoDB, it's database. Well, is it really a database? Is it a store? Is it state? So it makes naming more tricky. The advantages, there's a bunch of them. First of all, you don't have to remember to set up or tear down your mocks. So that's pretty good. It's entirely encapsulated as long as it's not causing any side effects. So you can run all your tests concurrently or in parallel. So that's great. it's a form of making your dependencies explicit. So even though JavaScript doesn't have a type system, now you can at least see, oh, well, it takes these things as arguments, probably needs them. And if it's not using them in the body, maybe it isn't using them, we can remove the argument. But the point is that it makes it fairly explicit how it works, for better or for worse. Yeah, so those are the pros and cons. So just to show you exactly what they look like, you can see same color coding. They look fairly straightforward. On a small function like this, there's no real downside to either of those approaches, but in a large code base, then the problems kind of compound. Especially if you've got lots of different services you're using, like HTTP requests or queues or databases or data time access, anything that's a kind of an external side effect that you might need to mock or swap out for something else. Mocking, to sum up, I would say it can be brittle and slow in reliability. Dependency injection can kind of melt into a murky, higher order function soup, especially in an untyped language. So there are downsides to both. But if mocking preserves your program structure but leaves your tests fundamentally more complex, and dependency injection changes your code under test, but makes your tests themselves conceptually simpler, is there a way to combine those approaches' strengths and get the best of both worlds? What if I told you there was, and almost all it required was the following diff? Can everyone see that? So we're swapping out our callback for a chain, whatever chain is, and then a then, promise.then, for another chain. But other than that, that's all we need to change in the code under test. And the question now is, well, what are we chaining here? Because it's not the arbitrary monad we were looking at before, it's something completely different. Well, the answer is that we're chaining something called a freer monad. This will take some explaining. So, freer monads. A freer monad, if I was going to explain it to you, I'd just say that it's the left adjoint of a forgetful operation. What's the problem? Yeah? And extensible effects are a fairly complicated category theory idea. I'm not going to get into the precise details, but you can think of them, especially for the purposes of this talk, as kind of lazy, nested placeholders for some kind of effect or monad that you may want to decide on later. So it allows you to defer decisions. It allows you to not have to make up your mind, which you may be thinking, oh, sounds a little bit like dependency injection or mocking. So yeah, get thinking along those lines. If you want to read the paper, you can. You can get all the grisly category theory details there. But in practical terms, it allows you to divide your program into what versus how. Okay, so your source code under test describes the what, and then your unit tests or your example tests would describe the how. Let's have a look at what that will, well, okay. The key thing before I go on to explain is that without this interpretation of going from what to how, they are completely useless. Okay, so you do have to, at some point, make up your mind. You have to say, well, I'm going to turn these into arrays, or I'm going to turn these into observables, or some other kind of data structure. Of course, we were using FastCheck for property testing, and there are a bunch of different extensible effect libraries for JavaScript. They're all in various states of completeness. I'm not sure if many of them are production ready. This one certainly isn't. This is one I've been working on. Called Runic, and it's inspired by a few different blog posts and libraries. I've kind of blended the ideas as best as I could. I've called it Runic because I like the way that freer monads have to be interpreted before they can be used, right? So it's like looking at this mysterious stone that's been etched with some strange symbols, trying to figure out what it might mean. In Runic, freer monads called runes, and like any other monad, a rune can be mapped over and it can be chained into another rune. Let's look at how to make them. So these are our dependencies from before. We're now using the Runic library. There's a function called etchRune, and you pass a value in, and you get back an inscribed rune with the value that you passed in. In exactly the same way, you might have a generator of a string or a promise of a date. This is now a rune of this object here. Having the type field there being a string, having that be some kind of unique database batch write or API response, that's completely up to you. You don't have to do it that way if you're working with rooms. That helps the TypeScript inference work if you're using TypeScript, but you can differentiate runes in whatever way you want, and we'll see how we do that later on. And in fact, talking about TypeScript, let's have a look at what TypeScript infers the type of our program to be. Remember, we've swapped out the callback and the .then for a chain. Let's see what TypeScript thinks it is now that we've got these dependencies. It's a lot of JavaScript, well, it's a lot of TypeScript. So at the top there, you can see we've created a few failure classes based on the error class, and we've annotated runes to say that, well, for example, if you've got a type of database batch write, it requires a table name, for example. It requires a series of items, have a title and a description, and then it can return any in this case, but you could be more specific. And that allows Runic to infer that our update function, its return type is a rune with 3 generic values. The first one is the union of effects that rune represents. Okay, so because we were handling put requests, and then we were writing to a database, and then we were sending a response back to the client, it knows that our effects that we're dealing with here are API put, or database batch write, or API response. I mean, it's not or, it's and, but this is the way you'd represent that. It's also able to infer that there are several failure cases of uncaught errors here. So you've got a network failure and a failed batch write. And then this is one of the possible success states. And in this case, I've picked it to mean something like, I don't know, the latency of sending a request back to the client, something arbitrary like that. So yeah, you can see it is able to infer exactly what your program is going to be doing and how it could fail and how it could succeed. One of the differences between Runic and a bunch of different extensible effects libraries I could find and read, and the literature, which I couldn't read, but I could find, is that there was no obvious way to handle runtime errors as far as I could see. There were first-class error handling mechanics, but nothing obviously analogous to, say, catching a rejected promise. So I've ended up kind of hacking this in. So runes are two-sided in the same way that a promise would be rejected or resolved. As I said before, runes are useless unless you interpret them into a target monad. So what's your favorite monad, everyone? If you can't decide, let's pick either. So the either monad. It represents a choice between two different things, a left and a right. That's typically meant to mean failed or succeeded. And in this case, we're using the fantastic Crocs library, which I really like. Let's just see what we can do with it. This is some really basic examples. Does that make sense to everyone? So you've got a left, that's like a failure state of the number 50. Mapping over it to add 5, okay? You then bimap over it, which allows you to apply a map to both left and right side, where we times by 10, or add 1 if it's a success, so a right-hand side, and we get back 500. Does that make sense? Shouldn't it be 550? Well, no, because maps only apply to the right-hand side, not the left-hand side. So it's doing 50 times 10 is 500. I think that's right. And now you've got the other example, which is you've got an either right, again of 50, mapping over it. This time it does apply, so it's now 55. Then you bimap over it, add 1, 56. So it's not timesing it by 10. That's pretty straightforward. Let's look at how we would interpret our rune into a bunch of either monads. Now, there's a lot going on here, so don't worry. Let's just read through it from top to bottom, starting with the green bit. So we're interpreting our update rune. That's just a function that runes have on them that allows you to convert them to other things. And we're checking, look, if the effect type is API put, we saw that before, then we want to turn it into an either write of a a bunch of example items. So this looks exactly like when we were mocking the API put handler and when we were dependency injecting it. I mean, they look kind of identical, really. Everything's just mixed around a little bit. We're then checking if the effect is a type of database batch write, then return a left of oh no. So that represents some kind of failure. The database failed to do its job. And then we then also check if it's an API response. We succeed with 42. Our latency here is 42, something like that. If we were to then write in our test body, check the actual result of our interpreted update rune, and we converted the left-hand side into an error and the right-hand side into itself, the identity function, then we'd get error, oh no. So you can see that this is pointing out that if we pass in, or rather, if we interpret our database write effect as failing, then our program does not handle that, and it propagates the error in exactly the same way that a rejected promise would propagate the error if you didn't have a .catch invocation, or a thrown exception would propagate up the stack if you didn't catch it. So that's good, but it doesn't give us much information about what the program was actually doing. It doesn't say how it tried to write to the database. It doesn't say what it sent to the client here as a response. So how could we get that information? Well, we can't really use an either. It doesn't have the capacity for that. Instead, we're going to look at a monad that might allow us to see what it's doing on the inside. This is the writer and state monad. Again, you can get it from the Crocs library, which is really good. Then you can use it to effectively, well, here's an example. Let's say you're doing a bunch of calculations, and every time you do one of these calculations, you want to log that you did the calculation and what time you did it. Okay? If you weren't using a writer or a state monad, then you would have to pass your log in through along with your calculations. So instead of doing 2 plus 2, it would now be 2 plus 2 and also add 4 to the end of this log. So this allows you to implicitly carry a log around with you and append to it whenever you like. Let's look at how that would work. I should say here that the writer monad specifically is for just appending to logs. The state monad is much more powerful, and it can remove, it can modify, it can change, it can even read from the state and have different behavioral changes based on that. We're going to look at the state monad pretending to be a writer monad here. So this is the using the state monad to build the shortest play in history after Beckett's breath, which is actually the shortest play. So that's very slightly shorter than this one. But this is the second shortest. So yeah, one thing I'm not showing you here is that they also allow you to carry around normal values with you, inside a state monad that isn't part of the state, because otherwise it wouldn't be very useful. You wouldn't be able to do any calculation with them if you just had the state. Does that all make sense? So we're modifying our log, adding hello, we're then adding goodbye, and we're starting it off with scene 1. So it ends up being scene 1, hello, goodbye. That makes sense to everyone? Yeah, cool. All right, let's look at how we'd interpret our rune into the state monad. So in this case, it's exactly the same as before, right? For our API put, we are, instead of returning an either, we're modifying our log, storing the fact that the effect came in. You can see that there, log concat effect. And then we're mapping it back into the items that we would have passed into our either. So they're really similar. If you flip back and forth, it would almost look like the same thing. Same thing with the database batch write. Here we're modifying the log, just adding the effect onto that log, and then sending a message of success. And the same thing for API response. So let's see what our test predicate might look like now that we have this log, this array of information, these objects. There we go. There's a lot going on there, so let's break it down. In this case, we've interpreted our rune into a result, which is a state monad, and then we're executing it with an empty array. That's going to get filled up with our effects, as before. And yeah, we simply filter that log for our effect types, because we're not interested in any of the others. There could be thousands, but we're interested in just these two. And then we just check that they match exactly what we expected them to match. So we check that we wrote to the database with buy hummus, but not the other item, because that didn't have a title, remember? And then we respond back to the client with buy hummus, and the one we didn't add was finish your Lambda Days talk. Because it doesn't have a title. There we go. So this allows us to inspect what our program is doing, even though our program doesn't return this as a value. It's just, these are side effects which are now being exposed by being implicitly stored in the state monad. So that's pretty cool in my opinion. Unfortunately, there's a couple of things missing. It doesn't allow you to simulate errors. An either allows you to simulate errors, state doesn't. But an either doesn't allow you to store state, right? So you're kind of screwed there. You could have used well, you can't really use a promise for various reasons I won't go into. But it would be really good if we had the feature set of state, the feature set of an either, and potentially even the feature set of other monads. Part 3. There we go. So this is, you may be guessing what's about to happen. We're going to combine the power of the state monad, which can remember what our program has been doing, the either monad, which remembers, or rather just represents, whether our program has crashed or succeeded, and the generative power of the arbitrary monad. And in this case, I'm going to have to, in this case, we're kind of in an awkward situation because famously monads don't really compose. You can have nested monads, so you can have a classic example is an array of promises or a promise of arrays. You can switch back and forth. But that's not the same as a promise array or an array promise. These two things being exactly the same thing. That sounds like an observable to me, but the point is that the semantics and the behavior of the monad really matters. There are these things called monad transforms that I won't go into, and also there are not really many JavaScript libraries for handling that kind of thing. So we're going to have to build our own custom monad that combines all these things together. I'm going to introduce that shortly. Let's have a look. Oh. There we go. This is the arbitrary state either. Okay, so I didn't want to call it the arbitrary state either because we'd be here all night. So instead, we're going to call it the ASE monad, ASE. It's instead of the ace of spades. This is the second worst joke. Instead of the ace of spades, you have an A's of strings. Yeah. There you go, good. This is the worst joke in the talk. Let's just be glad it's not an arbitrary reader state either. Yeah, there you go, good. All right, so let's look at how you would use the A's monad and what kind of features it can provide. This is fairly complicated, so let's go through it step by step. So an A's monad has to be given other monads that it then absorbs into itself and represents those. So let's start off with a generator of natural numbers. Okay, so this is fast-check, just generating any positive number, and maybe including 0, I'm not sure. And then we convert it into an A's. So now that's an A's of natural numbers. It's not an A's of an arbitrary, it's an A's of natural numbers. We then chain that into a state monad. We just put that number onto the state. So at that point, it's a state of, well, it's not a state of number precisely, it's a kind of a put state. And then we convert that into an A's. Okay, so now the A's has this state in it as well, and we can map that back into a number to get back to having an A's of a natural number. We then chain it one more time into an either left or right, depending on if the number is less or greater than 10, and then you just run it with 0. We're not using that state there, so 0 is just a placeholder. Let's sample it, because that returns an arbitrary generator. So we use fast-check sample on the result, and we get back these three things. Now, these would be totally random. This is just when I ran it yesterday. But you've got a left of 8, a right of 37, because it's it's greater than 10, and you've got a left of foo, 2. The salient point here is this is the state. Okay, the numbers are not the values, they're the state. The value is on the left here. Okay, let's have a look at interpreting our Rune monad into an A's monad. We can see our arbitraries here. So this is our database batch write effect. We're taking in the items that were written into the database. We're creating a subarray of those, a random subarray that actually would be from 0, so it could be an empty array, all the way up to the length of the array -1. So it will always be slightly smaller or a lot smaller than the original array. We've got a state monad here where we're just storing that subarray into the state. And actually what we're doing here is we're getting the difference between the items passed in and the subarray. Okay? So this is representing a database that is sometimes unavailable. Okay? So let's say you put in 10 items. It will write 4 of them to its storage. And then it will say, oh, sorry, those other 6, I couldn't process them. Too busy, don't have enough capacity. Yeah, and then it's doing the same thing there. It's just logging the fact that the event was even emitted. Now let's look at it being those separate monads which we already understand. Let's have a look at how they get absorbed into the A's monad. So the arbitrary is just being used like normal. And the state is going into the A's and mapped back into a normal event. If we didn't do this mapping here, then our database write request, when you then chained it inside your source program, would have no value. It'd be passed undefined. So we've got to make sure we're mapping back there. So you can see that this is actually really straightforward, right? There's not a lot going on here. It looks pretty dense, but it's just combining these two things that we already know how to use. Okay. This is our test body now. And because we know exactly what's being emitted by our program, written to the database or sent back to the client, we can actually start writing tests based on that information. Again, this looks fairly complicated, but effectively, all we're doing is we're checking that the log of our API put request, which has those items, remember that could be buying hummus if you're hungry, could be, I don't know, drinking a glass. It doesn't have to be about drinking water or eating hummus, it could be anything you want. But that represents the ones that were provided to our function, and we're checking that they're exactly equal to the items that were stored, because these state.stored items, that's what our state monad was adding before, concatenated with the items that our API response said weren't added. Okay, so what this is effectively saying is everything we give our function to store in a database should either actually get stored in the database or it should be spat back out because it didn't have a title or it was invalid or something. If those aren't equivalents, then our function is broken. It's not doing its job. Let's run our test and see what happens. Okay, our test fails. That's great. And why does it fail? Well, I've annotated the counterexample that FastCheck shows for you here. Again, this is our log, as you can see here. We had 2 items come in, example 1 and example 3. The database batch write took example 1 and example 3 in blue there, but didn't process example 3. So it spat 3 back out and said, sorry, I'm too busy to do 3. I've just done 1. And this is all randomly generated, remember. This is our arbitrary deciding, okay, you've given me this array of 2 things. I'm going to give you back a subarray of just 1 thing. And then our API response had, well, look, an added array of both those things and a not added array that's empty. So that's wrong. It doesn't make sense. That's not what we expected, right? Really, not added should contain example 3 at the very least. And FastCheck has generated these variations, and then our test runner is pointing out these are not equivalent. There's a mistake here. So let's see if we can fix this. And we'll fix it by first reminding ourselves of what the program looks like, because it's quite a while. Okay, so there you go. Remember, it's API put, update, change to a batch write, and then change to an API response. Let's fix this somehow. How are we going to fix it? Well, if we think that maybe sometimes writing to our database isn't successful, let's just do it twice, right? Let's just be a little bit more insistent. There we go. So we've just added an extra chain in there where we're saying, hey, look, if you failed the first time to batch write, just do it again. Just do it again. With, I should add, the unprocessed items. If you did it again with the original items, then you'd have duplicates in your database. And that could be something you could actually write a test for to make sure that you don't end up with duplicates. We don't have one of those, but you can just use your imagination to imagine a slightly better talk. So anyway, let's run our test again and see if that fixed our problem. Oh no, it's made it worse. There's more things now. That's weird. So why are there more things? Well, we were interpreting our batch write request into an arbitrary state either, an A's, that could pick random results. We were also doing off-screen the same thing with our API put requests. We were randomly generating items. What FastCheck has done here is it's enumerated probabilistically and found a simulated API put request service scenario where enough items were sent from our hypothetical user of our to-do app that the two batch writes, one after each other, could not handle everything. So let's say, let's hypothesize that maybe the first one wrote all but 2. That was the first 2 there. And then the second one had an unprocessed item of 2 more. So we called it again with those remaining 2, and it only wrote one of those. And the one it didn't write would have been Baz example 3. Okay, so it's found a situation where our hack to write twice in a row wasn't enough. So let's have another go at fixing it. We're going to go with the nuclear option now. We're going to go with a recursive batch write. Because if doing something once is enough, doing it twice is enough, let's just keep on doing it forever until it's enough. Now, in the real world, you'd probably want to have some kind of exponential fall-off or fallback to say, hey, if it's not working, let's slow down a bit and maybe let's stop trying after 10 or 50 or 100 times. This isn't the real world, so we'll just keep on doing it. And as you can see, this is fairly straightforward, right? We're just invoking our recursive batch write with our table name, our items, and then the definition for recursive batch write checks, hey, if you've got any unprocessed items left, just keep invoking yourself again and again and again. If you don't have any left, if the array is empty, then, well, we don't want to do another effect. We just want to say stop. And in the same way that, for example, a promise resolve doesn't actually make an asynchronous request or do anything side effecting. It just takes a value and stores it inside a promise in the same way that, well, you can do it with any monad. We're doing that with a rune here. So rune of doesn't represent anything. There'll be nothing to interpret there. It just means lift this value, inscribe it onto a rune. It effectively means stop. Stop being recursive. And then at the very end there, you can see we're now correctly taking our unprocessed items if the batch write, for whatever reason, stopped. Now, we know it would never stop, but let's say it stops for some reason. We would then send a request back to the API saying, hey, look, we were too busy. OK, let's run our tests again and see what happens. Oh my God, they passed. That's brilliant. So what's happening here is in the phase space of all possible databases that fail sometimes, because remember that, this took 1.8 seconds. Now that's actually quite a long time for a unit test to run. So that means that our test runner was working with FastCheck to try out a database that fails the first time, doesn't fail the second time, and then if it fails the first time, maybe it fails the third time, and it's trying all these different variations. Given that phase space of databases, it could not find a kind of adjoining phase space of API requests that could overload it that a recursive batch write couldn't help with. Hypothetically, imagine if you had a database that always failed, which we weren't simulating in this case, then it would still break. But this passed. That's great. Can we go further? Can we do better? Because a database that's sometimes unavailable, well, imagine if our databases were just sometimes unavailable. Sometimes they're like completely gone. They're broken. They're destroyed. So let's simulate that. So now we're going to introduce the either monad that we were using before, because A's can absorb either monads, and we're chaining it from a Boolean, okay? So we're generating random Boolean values, absorbing it into an A, so this is an A's of Boolean, and if it succeeded, I've graded this out so you can't really see, but we return our original, sometimes unavailable database phase space. If success is false, then we produce an error, and we actually return a completely broken database response. Yeah, you can see here, error, yes, return the error state, otherwise return the success state. So this will randomly flip between being broken entirely to just being broken some of the time. Let's see what happens. Oh, our test fail. That's not good. And you can see that the error that we were putting inside our left and turning into an A's has been propagated all the way through our program. That proves that our program doesn't have any error handling. So yeah, can we fix this? We can, and we can do it fairly straightforwardly just by appending an else or else clause, which is, again, this is a Runic method that is like promise.catch. And what it does is it simply catches any possible errors that could have been omitted by batch write or actually API response because of the way those things are chained in, but we're not simulating a failing API response in this case, and returns a status code of 500 and any unprocessed items that the error would have propagated. So yeah, we're going to then off screen make sure that our property test, that deep equality where we're saying, hey, any items you put in must be either written to the database or spat back out. Only check for that if you get a status code of 200. If you get a status code of 500, check for some other value, like make sure that, I don't know, there's always a reason of, a valid reason attribute with all of the items came back. Something that handles our error state. Let's run our tests and see what happens. Amazing, they pass. Great, so we're proving here that no matter what kind of failing database, no matter what kind of API requests we send in, we handle every scenario, and our function is now robust to a misbehaving database. Yeah. So in conclusion, why have I told you all this? Well, I wanted to prove that not only is kind of abstract functional programming possible in JavaScript, shock horror, but it can even fix traditional problems that you get with the kind of best practices of mocking or dependency injection. We can do better using clever ideas. And I also wanted to show you that property testing is usually used to treat inputs as value spaces, but actually we can extend that. We can treat our software's dependencies, our databases, our queues, our even dates and time access, anything that's a side effect, we can treat it as a phase space of the set of all possible failing databases, the collection of all possible queues that sometimes give you the wrong result. Yeah, so that's about it. Thank you.